Have you ever just looked at an object and wondered, how did they even make that? Well, today we're going to peel back the layers on everyday things, from simple toys to massive industrial tanks, and uncover the hidden geometry that's all around us. Let's dive in. So, take a look at these two things. We've got an oil tanker, which is basically a cylinder with some round ends, and then we have a spinning top. They look pretty familiar, right? But you'll notice, they aren't simple shapes like a cube or a sphere. They're actually what we call combinations of shapes.
So you gotta wonder, how would you actually measure them? I mean, if you had to paint that spinning top, how much paint would you need? And for the tanker, how much oil can it really hold? These are real-world questions, and they boil down to two key ideas: surface area and volume.
Well, the answer lies in one simple, really powerful secret. It's a kind of mental hack that turns these complex problems into something much, much easier. And what's the secret? You just have to break it down. Here's the big idea. Almost every complex thing you see is just a bunch of simple shapes we all learned about in school. Cylinders, cones, spheres, cubes, all stuck together. Seriously, think of it like building with geometric Legos. Once you can see the individual blocks, the whole structure starts to make sense.
So how do we actually do it? It's a super simple three-step method. First, you just observe the overall shape, like this toy top. Second, you identify the basic parts. Can you see them in there? And third, you calculate the details for each of those parts, which we'll get to in just a sec. And there it is. When you really look at that spinning top, you can see it's just a hemisphere on the top half and a cone on the bottom half, and they're just joined together at their flat bases. This is it. This is the core idea right here. We've deconstructed the complex thing into two simple parts. Okay, so now let's use this method for our first big challenge, measuring the outside, or what we call the surface area. Now this is where it gets pretty interesting, and there's one really important rule you have to remember.
First off, what even is surface area? The easiest way to think about it is this. It's the total area of all the surfaces on an object that you can physically see and touch. It's the part you'd have to paint. And here is the golden rule. When we combine two shapes, the surfaces where they're glued together, well, they get hidden. They're not on the outside anymore, so we can't count them in the new surface area. They've pretty much just vanished from view.
Now this right here shows the mistake almost everyone makes. You'd think you just add the total surface area of the cone to the total surface area of the hemisphere, right? But nope, that's wrong. Why? Because their flat circular bottoms are now glued together on the inside of the top. The right way is to add only the curved surface area of the cone and the curved surface area of the hemisphere. The flat parts don't count.
Okay, let's try another one. Here we've got a hemisphere sitting on top of a cube. Now, to get the surface area, you'd start with the total area of the cube, but wait, you have to subtract the area of that little circle where the hemisphere is sitting because it's covered up. Then you add the curved area of the hemisphere on top. See, it's a game of adding what's showing and subtracting what gets covered.
All right, let's switch gears and talk about measuring the inside, the volume. And I've got some good news for you. When it comes to volume, the rules get way simpler. In fact, the source material puts it perfectly. The volume of the solid formed by joining two basic solids will actually be the sum of the volumes of the constituents. Yep, no hidden tricks this time. It's true. Unlike with that tricky surface area, no space just disappears when you join two objects. The total internal space is just the sum of the individual spaces. So for that spinning top, you literally just add the volume of the cone to the volume of the hemisphere. It's as simple as that.
But this simplicity can also be used in some pretty sneaky ways. Check out this juice glass. At first glance, it looks like a normal cylinder, but there's a little secret at the bottom. The base has this hemispherical bump that actually rises up into the glass.
Now, if you calculated the volume of the glass as if it were a perfect cylinder, you'd get what we call the apparent capacity. In this case, that's 196.25 cubic centimeters. That's how much juice you think you're getting.
But we have to account for that sneaky little bump. That raised part takes up space. How much? A full 32.71 cubic centimeters. That's space where your juice can't go.
So to find out how much juice you actually get, we just subtract the volume of the bump from that apparent capacity. And the real amount is only 163.54 cubic centimeters. It's a perfect, if slightly deceptive example of volume subtraction at work.
So okay, this is a pretty cool mental puzzle.
But you might be asking, why does any of this actually matter in the real world? Well, it turns out this way of thinking, of deconstructing complex shapes, is absolutely essential to how we build and design our world.
I mean, this is not just some problem in a textbook. Engineers are using these exact principles to design rockets and complex machinery. Manufacturers use them to create things like medicine capsules. Architects use them to figure out the space inside a uniquely shaped building. It is truly everywhere, from something as simple as a bird bath to massive industrial equipment.
So if there's one thing to take away from all this, it's that once you learn to see the world this way, as a combination of simple, understandable parts, you unlock a whole new way of looking at things. You can look at almost any object and start to see the cones and the cylinders and the spheres hidden inside. So my question for you is, what hidden geometry are you going to discover today?